The complexity or runtime of algorithms is an important criterion for the selection of algorithms. In many cases, you need to choose which of many algorithms you will use to solve a certain problem. And if you're sensitive which runtime algorithms have and therefore which complexity, you will avert that a calculation never finishes. If a calculation never finishes, or if it needs a huge amount of time, you won't be happy either. The question is, how can I evaluate the complexity? There are different possible approaches. For example, you could think, I want to compare the memory usage of algorithms. But this is not really good. Nowadays, memory is very cheap. Therefore, it makes no sense. Another thought could be, I will look at the runtime in seconds. However, this depends on the machine being used. That is why we don't use this. Instead, we use the calculation steps, which an algorithm uses depending on the amount of input data. This is something we can use to measure the complexity of an algorithm. We will look at this using an example. Here we have a function. This function called sum is supposed to calculate a sum. And it receives a list from here, which contains numbers. This could, for example, be an array. And it will work through this list now. Because this is a for loop, we have a control variable called I, which counts from 0 to the length of the list. Therefore, it will use every single element of the list once. Then it will calculate the sum of all elements and return the result. It is clear that the function sum depends on the complete runtime, meaning the length of the list. That's why we use certain classes of algorithms in the so-called O notation. For example, this is the class of linear runtime. Thus, we have a dependency of n. N stands for the number of elements in the list. That means that I don't display the complexity of an algorithm in definite quantities. Instead, I say this is O of n, because there is a linear runtime. That depends on the value of n. Besides O of n, there are other classes of complexities. For example, there's O of logarithm to the base of 2n. Also, we have O of n squared and O of 2 raised to the power of n, and so on. Now we have found classes in which algorithms can occur. And of course, we always try to use an algorithm with a very small complexity to solve a problem, because then we will be finished faster. I want to show concrete examples. Here we have a specific amount of persons. These persons are not assorted if we take a look at the list above. Let's assume these persons are in one list. And our goal is to find the person whose height is exact 1 meter and 70 centimeters. I've already marked it here. This means we know it's this person. But of course, our PC doesn't know that. When he receives a list of persons, he has to look at every person at once. And this is the reason why the complexity of this algorithm, work through this list one after another, is linear, meaning O of n. We begin with the first one. We check if he is 1 meter and 70 centimeters tall. No, he's not. Then I check the next person. He isn't as well. The next person isn't that tall neither, but this one is exactly 1 meter and 70 centimeters tall. This means we have a linear runtime of O of n. In many cases, you don't only think about a specific case, but you think generally, what is the worst case? In the worst case, that can be seen below, the person we want is on the last position. But even in this case, the runtime is still O of n, because in the worst case, we just have to look through all n persons in our list to find our wanted person on the last position. Now, let's take a look at what's happening if we have a sorted list. Now we have a sorted list, which we can see this here. The biggest one is at the front, the smallest one at the back. Because of the sorting, we can use a different algorithm. This algorithm would have a runtime O of log 2n. And O of log 2n is much smaller than O of n. This means that the runtime, the complexity of the algorithm we can use, is much cheaper. This complexity is preferred in contrary to a linear runtime. Let's take a look at how this works. In this approach, we just choose the median element directly. To be more precise, we go to the right from the median element, we check what kind of size we found here. And here we can see, okay, this one here is 1 meter and 80 centimeters tall. We know that this list is sorted, so on the left side there are the people which are greater than 180. This means after looking one single time at the person we detected, we can basically declare the half of all people here as not interesting, because they are bigger than 180. Suddenly only the half of the list remains. Now we are going to the median of the remaining people. We may see, okay, someone here is 1 meter 60 tall. And we know we are looking for someone being 170 tall. So he can't be on the right side of our list. Thus, we can ignore these ones. From remaining 4 people, we cut 2. This algorithm would have a runtime O of log 2n. And O of log 2n is much smaller than O of n. This means that the runtime, the complexity of the algorithm we can use, is much cheaper. This complexity is preferred in contrary to a linear runtime. Let's take a look at how this works. In this approach, we just choose the median element directly. To be more precise, we go to the right from the median element, we check what kind of size we found here. And here we can see, okay, this one here is 1 meter and 80 centimeters tall. We know that this list is sorted, so on the left side there are the people which are greater than 180. This means after looking one single time at the person we detected, we can basically declare the half of all people here as not interesting, because they are bigger than 180. Suddenly only the half of the list remains. Now we are going to the median of the remaining people. We may see, okay, someone here is 1 meter 60 tall. In Latin, logarithmus dualis of n, and n is 8. In this case, the amount of steps would be 3. So let's take a look at the next complexity class by thinking about consuming ice cream. Namely, there's the case that we check out an ice cream cone with 2 scoops of ice. We can have 3 sorts of ice cream: vanilla, strawberry, and pistachio. Now, if we think how long do we need, using an algorithm that checks every combination once. To check that, we can have a cone with 2 scoops of ice cream, composed of 2 times vanilla. 1 times vanilla, 1 times strawberry, 1 time vanilla, 1 time pistachio. 1 time strawberry, 1 time vanilla, 2 times strawberry, 1 time strawberry, 1 time pistachio. 1 time pistachio, 1 time vanilla, 1 time pistachio, 1 time strawberry, and 2 times pistachio. Actually, this is a little bit stupid example because we basically have here a strawberry vanilla combination and a vanilla strawberry combination. But let's assume that it's interesting for someone which scoop of ice cream he eats first. Because one scoop is on the top of the cone, so it makes sense to distinguish that. But we can see if we have 3 sorts of ice cream, we indeed have to test 9 different combinations. Thus, we are in the complexity class of n squared. 3 times 3 equals 9. We have 3 sorts and we have to check 9 different combinations. If we increase the amount of scoops of ice cream to 3, we would go into a bigger complexity class. So the next complexity class I would like to show you is the class O of 2 of n. And I want to show you that on an example of the music. Assuming we have a music instrument, a piano. Such a piano has piano keys. Each of these keys below can be played. Now let's test this using an algorithm. If all of these sounds made by different piano keys sound well, or if there may be a combination of sounds which sound bad, so that we may have to repair the piano. Now we can play every single key and listen to them separately. But if we want to listen to a combination of different keys at the same time, we will have to think about the following. The first key has exactly 2 options. These are, we can play it or we don't play it. The second key has 2 options too. We can play it or we don't play it. The same with the third, fourth, and fifth, and sixth. That means we have 2 times 2 times 2 times 2 times 2 times 2 equals 2 raised to the power of 6. 1, 2, 3, 4, 5, 6 possible options. To make this piano sound using different key combinations. 2 raised to the power of 6 should equal 64. Now we have an order of 2 raised to the power of 6. The longer our piano is, the more keys it has. And the higher are the possibilities of sounds we can make. It's easy to figure out that if the number of there grows, so the number of keys, that the number of possibilities becomes very, very high. This complexity of the algorithm is very, very expensive. Now I want to contrast this to another example. Let's assume we have 2 algorithms. One algorithm has the order log 2 of n. The complexity class is also called order. And the other algorithm has the order 2 raised to the power of n. And let's assume a hypothetical list that needs to get processed, or keys that have to get processed, of n equal to 70. Then we can think, how many steps do we need in the respective order classes? At log 2 of n we need 6.1 steps. So 2 raised to the power of 6 is more or less 70. Of course, we can't do 0.1 execution steps, so we are spending 7 steps. Now, if we think that we need 1 millisecond for executing a single step, this means we need 7 milliseconds for an algorithm of the complexity class of the order log 2n. Let's try that using algorithm B to count how many steps we need. So this is 2 raised to the power of 70, and this equals 11.8 times 10 raised to the power of 20. This means there are 20 additional zeros behind. That's a huge number. And if we consider that we need 1 millisecond per step, we have to ask how many minutes this takes. We will find out, if we calculate this, that this is twice the age of our universe, meaning 37 billion years. Now it's clear that we can't use algorithm B, because if we use that, handling an input size of n equal to 70, we probably would wait a very, very long time. In software engineering informatics, the complexity of algorithms is used to decide which algorithms are the preference. The algorithms create the same output in the end, but they need a different amount of runtime. The order we talked about today is a possibility to distinguish these algorithms according to their complexity, leading to the right choice.